Specific heat. Now, we've all had experience with this, especially if we have a frozen pizza. We put it inside the oven. We're excited. We're so excited to eat it. And we just cannot wait. After 10 minutes, we said, oh, I'm so hungry. It looks like the cheese is melted. I'm just going to come in and eat it. I take a bite, and lo and behold, it is cold. The sauce is freezing cold. All right, you ticked off. You put it inside for 30 minutes. Now we're starting to talk here. We take out a piece of pizza, we take a bite, and what happens? We are burned hot. That sauce is scorching hot. Wow, it's just really burning us. What happened? The cheese isn't really that hot, but the sauce is. So we say, okay, we're going to let it cool. We're really excited to eat this pizza. Just going to let it cool. Now we're going to take a little bite of it. And what do we see? The cheese is cold, but the sauce is still hot. What's going on? What up with that? So the sauce is mostly water. The water has a high specific heat capacity. So if something has a high specific heat, it's going to retain that heat longer. Another example, let's say you want some soup. It's a nice hot day out, nice cold day. You're going to eat some soup. So you heat it up and you go ahead and taste it after a few minutes. And it's a hot metal pot and cold soup. What up with that? Seriously. How come the pot is hot, but the soup is cold? So you go back to heating it up for a while. Start heating it up for a good 30 minutes. And it's hot pot, hot soup. But then you cool it for 10 minutes and it's a cold pot and hot soup. Seriously. Now the reason is because the metal has a low heat capacity and water has a high heat capacity. Now heat capacity is the amount of energy that a material can absorb before a noticeable change in temperature results. What does that mean? Well, let's look at an example. So we had the pizza. Okay, so we had that pizza. If we look at a cross section of that pizza, here we have the crust. Up here, the cheese. And inside here, it was the sauce. The sauce contains mostly water. And we noticed that the cheese seemed pretty hot at first. It was melted, but the sauce was actually pretty cold. The sauce was mostly water. The sauce had a higher heat capacity. The sauce absorbed a lot more energy, a lot more heat before you noticed any difference. Whereas the cheese or the crust, it didn't absorb that much heat and you could notice a difference. It was actually pretty cold or pretty warm. So it didn't have to absorb that much energy before you noticed the difference. Whereas with the sauce, you did. Same thing with the pan. We had the water. It took a lot of heat to be absorbed, before we noticed a difference. Whereas with that aluminum pan, it didn't take much heat before we could feel it. So with a high heat capacity, it absorbs a lot of heat. The substance will absorb a lot of heat before you notice something. And that's water has a high heat capacity because it will absorb a lot of heat before you notice a difference. Whereas aluminum or metals have a very low heat capacity. You will notice a difference right away. You get a little heat there, you'll notice a difference. You will feel a difference. Now the thing also is that if you absorb a lot of heat, you will hold on to a lot of heat. You will hold on to it, or the substance or material will hold on to the heat longer than those that don't absorb that much heat. So the water, if you heat up some soup, that water will hold on to that heat much longer than the aluminum can will, or the aluminum pot. So things that heat up quickly will cool down quickly. Things that heat up slowly will cool down slowly. Now, specific heat capacity is really just a numerical or a measurement of that heat capacity. And we look at that as a CP. That's the amount of energy of 1 gram needed to absorb in order to raise the temperature 1 degree Celsius.
And we can find the specific heat by this formula. C equals Q, which is the heat in joules that are supplied, and M, mass times delta T. So delta T is just T2 minus T1. That's the change. Change in temperature. Anytime you see delta, that's change. We had a sorority in when I went to college. Delta, delta, delta. It was change, change, change. C is something you can figure out. C we can usually look up in a table. So here's the value of C, specific heat capacity. Here we can see the specific heat capacities in joules, but also in calories per Celsius or calories per Kelvin. Here's joules per Celsius or joules per Kelvin. We can see water up here has a very high heat capacity. It means it can hold heat very well. That's why water is a great place to live for living organisms like fish. It holds heat very well. That's why it doesn't freeze over the summer, or excuse me, the winter. You'll have these little fishies, and on top in the winter there's be ice, so you can go ice skating on it and stuff like that. Because water has a high heat capacity, it holds onto that heat, whereas above it's freezing out, down below it's nice and toasty. And if we look down here though, lead, look how small lead is. That lead has a very low heat capacity. It heats up very quickly, and it cools down very quickly as well. All these metals here are very good conductors. They conduct heat. They take heat quickly and heat leaves very quickly. These metals, the stuff that we cook with, has a very low heat capacity, doesn't hold on to heat very well. And that's good if you're going to cook with something, because you want that heat to be transferred from the flame to the pot. From the flame to the pot to the food. Okay? You don't want something to hold on to that heat and not go to the food. We want that heat to be transferred quickly to that food. So here we see all those different heat capacities. It's kind of interesting to think about. Here's some other specific heat capacities. It's table 17.1 in your book. Pretty cool. So we can figure out this fun problem. How many kilojoules of heat are absorbed when 1 liter of water is heated from 18 degrees to 85 degrees Celsius? So how do we go about looking at this? Well, let's just write everything down that we're given. So we want to know heat. How many kilojoules of heat? How many kilojoules? 1 liter. Well, 1 liter, that's a volume. And then 18 degrees to 85 degrees. Well, that's a temperature. Temperature 1 is 18 degrees Celsius. Temperature 2 equals 85 degrees Celsius. All right, so we were given that equation, Q over M delta T. Well, we want to solve for Q, so we'll rearrange the formula to be Q equals MC delta T. And one way everyone always remembers this, especially in college, is that if you're going to or plan on going to med school, you have to take the MCAT. So we have MCAT here, and heat, there's a lot of heat when you take the MCAT. It's a difficult test, and med schools will really look at that in order to grant you admission. So some of you guys will be taking that in a few years. Let's look. Well, we're solving for Q. We have delta T, because that is just T2 minus T1, which is 85 minus 18, which equals 67 degrees Celsius. So that's change in just a difference, so we don't need this. So we have delta T. C, we can look up in a table, the specific heat. M is the mass. Well, we're given a volume. We're not given mass. Well, the cool thing is, I know that 1 milliliter of water, since it's water, equals 1 gram. So that's a direct volume to mass relationship. So if we have 1 liter, we can figure that out, because 1 liter is 1,000 milliliters. 1,000 milliliters will thus then equal 1,000 grams. And then we have our mass here, 1,000 grams. So we can just plug everything in. Let's change 1,000 grams to 1 kilogram. It makes it easier. 1 kilogram. Makes it much easier. C. What is C going to be? We'll put temperature in here. Well, we'll look at those tables. Let's see. Which one should we use here? Let's look at the difference here. We have joules, kilogram, Celsius, or we have this one, which is joules, gram, Celsius. And this is 4.18. So it really depends on the unit we're using. We're going to use kilograms, so let's use that specific heat with the kilogram in it. 4186. So that's going to be 4186. Just plug it in the calculator. I will do it in my head. So carry the 2. That is going to be 2.80 sig figs times 10 to the 5 joules. But we want kilojoules. So that means we have to divide by 3. If we divide by 3, that's going to be 2.80 times 10 to the second kilojoules. So that is a lot of heat produced just from 1 liter of water. If you just heat up 1 liter of water from 18 degrees, so that's 1 liter of water is about a quart of water. We heat that up from 18 degrees to 85 degrees, not even boiling. It took this much kilojoules, or this many joules, to heat it up. Now, for the sake of argument, let's say we want to know kilocalories. So we'll just use the same formula, Q equals mc delta T. We know that the mass is 1,000 grams. Delta T we found out to be 67. What about C? What is specific heat? Well, we want to know calories, so we're going to use this. Calories, 1. So this is going to be easy, much easier. C will be 1. That equals 67,000 little calories. So that's in little bitty calories. It's not in the big food calories, but we want to know how many food calories that will be. So that's kilocalories. We just divide by 1,000 and we'll get 67 big calories. It will take about 67 food calories, 67 calories that you eat, to heat up a quart of water from 18 to 85 degrees Celsius. That's not even boiling, that's just to warm it up.